Welcome viewers. In this video, we'll see the solved problem in the magnetic circuits part 1. Subscribe this channel for more electrical related videos as well as the course material. The course material drive link is available in the description box. Now we'll go to the problem 1. A solenoid is wound with a coil of 200 turns. The coil is carrying a current of 1.5 amperes. Find the value of magnetic intensity when the length of the coil is 80 centimeter. So the given data are the number of turns is given 200. Current is 1.5 ampere. The length is 80 centimeter, that is equal to 80 into 10 to the power minus 2 meter. Now all the data are available. Now we can go to the magnetic field intensity. The magnetic field intensity H equal to Ni by L. Very simple formula, very simple problem. It's a direct substitution only. The all data are available. N available, I available and L available. So all the values are substituted. After simplifying this, we got the magnetic field intensity equal to 375 ampere turns per meter. The unit for magnetic field intensity is ampere turns per meter. Now we'll go to the second problem. The magnetic strength of a magnet with a square cross section of side 5 centimeter is 0.3 milliweber. Find the value of magnetic flux density. So the flux is given 0.3 milliweber. 0.3 milliweber means milli means 10 to the power minus 3. So 0.3 into 10 to the power minus 3 Weber. Then area of cross section. This 5 centimeter side is given. So the area is side into side, 5 centimeter into 5 centimeter. So the centimeter is converted into meter by multiplying 10 to the power minus 2. So 5 into 10 to the power minus 2 into 5 into 10 to the power minus 2 meter square. That is nothing but 25 into 10 to the power minus 4 meter square. Right? The square is given, so side is given. The area of the square is side into side. Now we'll go to the magnetic flux density. Magnetic flux density is nothing but B equal to pi by A. The flux density is nothing but flux per unit area. B equal to pi by A. The pi value is available. 0.3 into 10 to the power minus 3. Then area we calculated 25 into 10 to the power minus 4. By simplifying we got 0.12 Weber per meter square. The unit for magnetic flux density is Weber per meter square. So we got the value 0.12 Weber per meter square. Now we'll go to the third problem. A current of 2 ampere passes through a coil of 350 turns wound on a iron ring of mean diameter 12 centimeter. The flux density established in the ring is 1.4 Weber per meter square. Find the value of relative permeability of a iron. So what are the data given? First the current is given 2 ampere. Current equal to 2 ampere. Number of turns 350. Magnetic flux density B equal to 1.4 Weber per meter square. Mean diameter is given 12 centimeter. So that mean radius equal to 6 centimeter. So the mean length is nothing but L equal to 2 pi Rm, circumference. Circumference of the ring is nothing but a length. L equal to 2 pi Rm. The circumference is nothing but length. So the Rm value is available. So 2 into pi into Rm, 6 into 10 to the power minus 2 meter. 6 centimeter is given. So while converting it become 6 into 10 to the power minus 2. So by simplifying we got 12 pi into 10 to the power minus 2 meter. Right. So the length is nothing but circumference. The circumference of the length is nothing but the circumference of this ring is nothing but the length. And also we have mu naught, it's a constant, absolute permeability, 4 pi into 10 to the power minus 7. We need to find the relative permeability of a iron. Right. So the one length is equal to circumference. Both are equal. In order to find the relative permeability, first we will go with the magnetic flux density because this value is given. B is available. B equal to mu into H, that is mu naught mu r into H. The relation is available, the relation between B and H. Now the H is replaced by Ni by L, magnetic field intensity equal to Ni divided by L, right. So from that we can find what we need is mu r. So bring other terms in the left hand side. So the L is multiplied here, B into L. This mu naught Ni is brought in the denominator because we need this value, right. So other values are brought in the left hand side. So B into L divided by mu naught Ni, that is mu r equal to this expression. Now we can substitute the value here. B is 1.4, length is we calculated 12 pi into 10 to the power minus 2, mu naught is constant, absolute permeability 4 pi into 10 to the power minus 7, the number of turns is 350 and the current is 2 ampere. So by simplifying this, what we got, mu r equal to 600. The relative permeability of the iron ring is a 600, mu r value is 600. Now we will go to the fourth problem. A mild steel ring of mean circumference 60 centimeter have a cross sectional area 4 centimeter square is wound with a coil of 300 turns around it. Calculate the current required to produce a flux of 500 microweber. 500 microweber. Take the relative permeability of the iron is 400. Now we will see what are the data available. The mean circumference is given 60 centimeter. We already discussed in the previous problem also. The circumference is nothing but the length, L equal to 2 pi r because of circular ring. The length and circumference are equal. So L equal to 60 centimeter. The circumference is directly given 60 centimeter. So converting into meter, it is 60 into 10 to the power minus 2 meter. So the length of the magnetic path is nothing but 60 into 10 to the power minus 2 meter. Now what are the other data given? Number of turns given 300. The flux is given 500 microweber. So 500 into 10 to the power minus 6 Weber. Micro means we have to multiply with 10 to the power minus 6. Milli means 10 to the power minus 3. Micro means 10 to the power minus 6. Then mu r value is given 400. Relative permeability of the iron is 400. The area is given 4 centimeter square. While converting meter square, 4 into 10 to the power minus 4 meter square, right? Centimeter to meter, 10 to the power minus 2. Here centimeter square is there, so 10 to the power minus 4. Now we will find the current value. The flux is given. The main thing is the flux is given. From that we need to find the current. So we start with the flux. Pi equal to Ni by S. That is the reluctance S equal to Ni by pi. From that we got the formula pi equal to Ni by S. Ni divided by this S. Reluctance, one more formula is L divided by mu naught mu r into A. The reluctance, one more formula available in terms of length and area. Like R equal to rho L by A. Similarly S equal to L divided by mu naught A. L by A is common. There rho is there, resistivity, here mu available in the denominator. Right. So this mu naught mu r A will go to the numerator. It is available in denominator, so it will go to numerator. Ni mu naught mu r A divided by L. So here only we need the L value. So bring this L I value. We need current. So this L is multiplied here, pi into L. This N mu naught mu r A is brought in the denominator in the left hand side. So that I equal to, we got this value, pi L divided by N into mu naught mu r into A. Now we will substitute these values one by one. So the pi is given 500 microweber, 500 into 10 to the power minus 6. The length is nothing but circumference is given 60 into 10 to the power minus 2 divided by number of turns is 300. The mu naught, absolute permeability is constant, 4 pi into 10 to the power minus 7. The mu r, relative permeability iron, is given 400. The area is given 4 centimeter square, that is 4 into 10 to the power minus 4 meter square. So by simplifying all this, we got I equal to 7.464 ampere. For a given flux, the current required is nothing but 7.464 ampere. So in this video we discuss the 4 simple problem based on the magnetic circuit. Few more problem available in the other videos. The link is given in the description box. Also subscribe the channel for more videos. Thank you. Welcome viewers. In this video we will see the solved problem in the magnetic circuit part 2. Subscribe this channel for more electrical related videos and course material. Course material drive link is available in the description box. Now we'll go to the first problem. That a toroidal air cored coil with 2000 turns has a mean radius of 25 centimeter. This mean radius is nothing but the core. Core mean radius is 25 centimeter. The diameter of each turn is being 6 centimeter. This diameter is nothing but diameter of the coil. This radius is the radius of the core. If the current in the coil is 10 ampere, find the value of mmf, flux, flux density. These 3 parameters we need to find. So the data is given, the number of turns is given 2000. The current is 10 ampere. The mean radius of a core 25 centimeter. So 25 means 25 into 10 to the power minus 2 meter. Centimeter is converted into meter. The diameter of the coil is 6 centimeter. So the radius of the coil is 3 centimeter. So 3 into 10 to the power minus 2 meter. Well, this centimeter is converted into meter. Now we'll go to the parameters one by one. First we will find the mmf. mmf is nothing but n into I, number of turns into current. Right? The number of turns given as 2000, current is 10. So it is 20,000. The unit is ampere turns. The unit for mmf is ampere turns. So 20,000 ampere turns. Next we will find the flux. Flux equal to, the formula for flux equal to mmf divided by reluctance. The normal formula is reluctance equal to mmf divided by flux. From that, flux equal to mmf divided by reluctance. So first we will find the reluctance. Reluctance, one more formula available, L divided by A into mu. Like a resistivity, we have the reluctance formula L divided by A mu. The L is nothing but the circumference, because it is a toroidal coil. Toroidal means circular form. So the length of the core is nothing but circumference of the core. L equal to 2 pi Rm. This Rm value is given. The A is nothing but area of the coil. This L refers the core, length of the core. This A refers the area of the coil, pi r square. The R value is given. Diameter is given. From that we can calculate the R. Right? So this Rm refers the radius of the mean radius of the core. This small r refers the radius of the coil. Then mu naught, mu r. Right? So this pi value got cancelled. So that 2 Rm divided by r square mu naught into mu r. Now we can substitute the values. So 2 into the Rm is 25 into 10 to the power minus 2. Then r square is 3 into 10 to the power minus 2 square. The mu naught is constant, 4 pi into 10 to the power minus 7 into relative permeability is 1. Not given in the problem. If it is not given, we can assume that it is a air cored. So that the value is 1. Yes, given as a air cored. For a air core, the mu r value is 1. So after simplifying, we got 4.46 into 10 to the power 8 ampere turns per Weber. Now the reluctance value is calculated. Right? So the reluctance value available, mmf we already calculated, so that we can calculate the flux. So flux equal to mmf divided by reluctance. So 20,000 divided by 4.46 into 10 to the power 8, what we calculated here. So that is equal to 4.48 into 10 to the power minus 5 Weber. The flux is nothing but 4.48 into 10 to the power minus 5 Weber. Now we'll go to the third one, flux density. Flux density equal to flux per area. Flux density means it is flux divided by area, pi divided by A. So the flux what we calculated now, 4.48 into 10 to the power minus 5. Divided by area is pi r square. Pi into r value is 3 into 10 to the power minus 2 square. So after simplifying, we got 1.6 into 10 to the power minus 2 Weber per meter square. The flux density, the unit is Weber per meter square. Now we calculated all three parameters, mmf, flux and flux density. Now we'll go to the second problem. The flux produced in the air gap between two electromagnetic poles is 5 into 10 to the power minus 2 Weber. The flux is the flux value that is between the air gap of two electromagnetic poles. The cross sectional area of the air gap is 0.2 meter square. Then we need to find what is the flux density, magnetic field intensity, reluctance. Also mmf dropped in the air gap and the given length of the air gap is to be 1.2 centimeter. For this air gap we need to find the mmf also. Now we will see what are the data available. So the pi value is given. Flux in the air gap 5 into 10 to the power minus 2 Weber. The area is given as 0.2 meter square. Mu r equal to 1 because it is air core. The length is given, is length 1.2 centimeter. That is 1.2 into 10 to the power minus 2 meter. Then mu naught is constant, absolute permeability 4 pi into 10 to the power minus 7. So these are all the data available. Now we'll find the value one by one. Flux density. Flux density B equal to pi by A. Flux per unit area. The pi value is 5 into 10 to the power minus 2. The area is 0.2 is given. The pi value and area value. So by simplifying this, what we got? 0.25 Weber per meter square. The flux density, the unit is Weber per meter square. Now we'll go to the magnetic field intensity. Magnetic field intensity H equal to B divided by mu naught into mu r. This relation is available. B equal to mu H. From that H equal to B divided by mu naught mu r. So the B value we calculated here 0.25 Weber per meter square. The mu naught is constant 4 pi into 10 to the power minus 7 into relative permeability is 1. So after simplifying we got 1.9894 into 10 to the power 5 ampere per meter. The flux density also calculated. Now we'll go to the reluctance in the air gap. The reluctance S is formula is L divided by A into mu. Here Lg, because of air gap it is Lg. Length of the air gap, area of the air gap. Right? The length is given 1.2 into 10 to the power minus 2. The area is 0.2 meter square already given. Mu is nothing but mu naught into mu r. Mu naught is 4 pi into 10 to the power minus 7. Mu r equal to 1. So by simplifying this we got 47,746.4 ampere per Weber. So the reluctance in the air gap is 47,746.4 ampere per Weber. Now we'll find the mmf in the air gap. Pi into reluctance. So reluctance equal to mmf by pi. So that mmf equal to pi into reluctance. So the pi value we calculate, a pi value is given 5 into 10 to the power minus 2. And this reluctance value we calculated 47,746. So by simplifying we got 2,387 ampere turns. So now we calculated all the parameters: flux density, magnetic field intensity, reluctance in the air gap, mmf in the air gap. Some more problem available in the magnetic circuit. The link is given in the description box. Also subscribe this channel for more videos. Thank you. Welcome viewers. In this video we will see the solved problem in the magnetic circuit. It's a part 3. More problems available and other videos available. The link is given in the description box. Subscribe this channel for more videos. Then drive link also available in the description box. We'll go to the first problem. A ring has mean diameter of 15 centimeter and a cross sectional area 1.7 centimeter square and has a radial air gap of 0.5 millimeter cut in it. So this diameter area is related to the ring, iron ring. It is uniformly wound with a 1500 turns of insulated wire and a current of 1 ampere produces 0.1 milliweber across the air gap. Calculate the relative permeability of the ion on assumption that there is no magnetic leakage. Now we will see what are the data available. The flux is given 0.1 milliweber, so it is 0.1 into 10 to the power minus 3 Weber, that can be written as 10 to the power minus 4 Weber. This 0.1 all, by including this 0.1 we can write 10 to the power minus 4 Weber. The area given as 1.7 centimeter square, so that 1.7 into 10 to the power minus 4 meter square. The centimeter is converted into meter. The air gap length is given 0.5 millimeter, so that is 0.5 into 10 to the power minus 3 meter. The diameter is 15 centimeter, so that radius equal to 7.5 centimeter, diameter divided by 2. The length is given 2 pi rm, L equal to 2 pi rm. So this rm is given. The length is equal to the circumference. Circumference of the core is equal to the length of the magnetic circuit, because available in a ring form, a circular form. So that length is equal to circumference. This rm value is given, is 7.5 centimeter. So 7.5 into 10 to the power minus 2 meter. After simplifying, we got 15 pi into 10 to the power minus 2 meter. So these are all the data available. Now we'll find the values one by one. We need to find the relative permeability of the ion. First we will find the magnetic flux density B for a air gap. B equal to pi by A. Pi is given 10 to the power minus 4 divided by A is 1.7 into 10 to the power minus 4. So after simplifying, we got 0.5882 Tesla. The magnetic flux density is calculated. Now we'll go to the magnetic field intensity. H equal to B divided by mu naught. That is B equal to mu H. From that, H equal to B divided by mu naught. We need to find mu R. This is for air gap. Mu R is 1. For air gap, it is 1. So B value we calculated 0.5882 divided by mu naught value is nothing but the constant absolute permeability 4 pi into 10 to the power minus 7. So after simplifying, we got 4.681 into 10 to the power 5 ampere per meter. The magnetic field intensity also calculated. Now we'll find the ampere turns for a air gap. N into I, ampere turns for the air gap. H into Lg. So H we calculated 4.681 into 10 to the power 5. The length of the air gap is 0.5 millimeter, that is 0.5 into 10 to the power minus 3 meter. So after simplification, we got 234.1. The ampere turn required for air gap is 234.1. Now we'll go to the total MMF required. So the total MMF required is 1500 into 1, that is 1500. So at the ion path equal to, this is the total magnetic field, the total ampere turns required available. From that, if you subtract this air gap, we will find the MMF available in the ion path. Net ion path will be 1265.9. So this is the total MMF available. From that, if we subtract the ampere MMF in the air gap, we will get the remaining value. The length of the ion path is 15 into pi into 10 to the power minus 2 minus. From the total length, we need to subtract the length of the air gap. This is the total length, 2 pi rm. From that, the length of the air gap is subtracted. So that 47.074 into 10 to the power minus 6 meter. Now we calculated the length of the ion path as well as magnetic ampere turns available in the ion path. From that, we can find the magnetic field intensity of the ion path. So far what we discussed is the air gap. Now it is for ion path. H equal to Ni divided by L. Ni is nothing but this value. From total MMF, we subtracted the MMF available in the air gap. So this is the MMF available in the ion path. divided by length. Length also we calculated. From total length, air gap is subtracted, we can get the length of the ion path. So by simplifying this, what we got? 2689.17 ampere per meter. So from this H value, we can able to find the mu R value. B equal to mu H, mu naught mu R into H. From that, mu R equal to B divided by mu naught H. Right. So this mu naught and H is brought in the denominator. So the B value we calculated is 0.882. We already calculated the B value. Divided by mu naught is constant, 4 pi into 10 to the power minus 7. And the H value we calculated here 2689.17. By simplifying this, we got mu R, relative permeability of the ion is 174. Now we calculated the value. We will go to the second problem. An iron ring has cross sectional area 400 millimeter square. Mean diameter 20 centimeter. These two refers the iron core. It is wound with 500 turns. The value of relative permeability is 250. The total flux set up in the ring. We need to find the total flux. The coil of the resistance is given 480 ohm and the supply voltage is 240. Now we will see what are the data available. The area is given 400 millimeter square. While converting meter square, it is 10 to the power minus 6. 400 into 10 to the power minus 6 meter square. And mu R value is given 250. Mu naught is constant, absolute permeability, 4 pi into 10 to the power minus 7. The voltage is 240 voltage. The resistance of the coil is 480 ohm and number of turns is 500. The diameter is given 20 centimeter. So that radius will be diameter divided by 2, 10 centimeter. That is equal to 10 into 10 to the power minus 2 meter. Now we will find the value one by one. First we will find current flowing through the coil. Our final aim is we need to find the flux produced in the air gap, flux produced in the ring. For that, first we will find the current. I equal to V divided by R. Very simple formula. V is given 240, R is 480. So that 240 divided by 480, 0.5 ampere. Now we will find the mean length of the magnetic circuit. L equal to 2 pi R. The length is nothing but circumference. Because of the ring in the circular form, the length is equal to circumference. So 2 pi into R is given. Diameter is given 20 centimeter. So R equal to 10 centimeter. While converting meter, it is 10 into 10 to the power minus 2. So by simplifying, we got 0.62831 meter, the length of the magnetic circuit. Then we will find the magnetizing force, that is magnetic field intensity, H equal to Ni by L, because now L is calculated. I also we calculated. So 500 into 0.5 ampere divided by L is 0.62831. So by simplifying, we got 397.887 ampere turns per meter. Now the magnetic rising force, magnetic field intensity also calculated. Now we will find the, from this magnetic field intensity, we can find the magnetic flux density B. B equal to mu H. The relation is available. So B equal to mu naught mu R into H. Mu naught is constant, 4 pi into 10 to the power minus 7. Mu R is given 250. Then the magnetic field intensity is now calculated 397.887. So by simplifying, we got 0.125 Weber per meter square. The unit for magnetic flux density is Weber per meter square. So from the flux density, we can able to find the flux in the magnetic circuit. Pi equal to B by A. That is B equal to pi by A. So that pi equal to B into A. So this B is calculated 0.125 Weber per meter square. And the area given as 400 millimeter square. So that is 400 into 10 to the power minus 6 meter square. So by simplifying, we got 50 into 10 to the power minus 6 Weber, or we can take it as 50 micro Weber. So we calculated the flux in the ring. So more problems available. The link is given in the description box, and also subscribe the channel for more videos. Thank you. Welcome viewers, in this video we will see the solved problem in the magnetic circuit part 4. Some more problem available in the other part. The link is given in the description box. Subscribe this channel for more videos and course material. The course material drive link also available in the description box. Now we will go to the problem 1. An iron ring prepared from a 10 millimeter bar has an average diameter of 8.3 centimeter and is wound with 598 turns of copper wire. A current of 0.975 ampere is sent through it. Find the flux established by the current. The take mu r, relative permeability, equal to 875. So we need to find the flux developed. The data is given is number of turns is given 598. The current is 0.975 amperes and the mu r value is given 875 and mu naught is constant 4 into 10 to the power minus 7. The diameter is given 8.3 centimeter, diameter of the iron ring. So that radius equal to 8.3 divided by 2, 4.17 centimeter, 4.15 centimeter. So while converting meter, it is 4.15 into 10 to the power minus 2 meter. So our aim is to find the flux density, find the flux established in the iron. So first we will find the area of cross section. The radius is given, so area equal to pi r square, pi into r, r is 10 into 10 to the power minus 3 square divided by 4, that is equal to 7.85 into 10 to the power minus 5 meter square. Right? So the average diameter is given 7.85 into 10 to the power minus 5 meter square. Then we will find the average length of the magnetic path. Average length of the path is nothing but circumference of the ring. Circumference of the ring is nothing but the length, L equal to 2 pi r. So 2 into pi into 4.15 into 10 to the power minus 2. So this radius refers the radius of the ring. This radius refers the radius of the coil, pi r. So by simplifying this, we got L equal to 0.267 meter. The length of the magnetic pole is calculated. Now from that we can easily calculate the flux available in the magnetic path. Flux equal to mmf divided by reluctance. The mmf is nothing but N into I. Reluctance we can write L divided by mu naught mu r into A. The formula is available. So this mu naught mu r A will go to the numerator. So N into I mu naught mu r A divided by L. Now we will substitute the values one by one. So the N is nothing but 598 number of turns. The current equal to 0.975 amperes. Mu naught is 4 pi into 10 to the power minus 7. Mu r value is given 875. The area what we calculated 7.85 into 10 to the power minus 5. The area we calculated divided by the length of the core is 0.2607. So by simplifying this, what we got 0.193 milliweber. Milli means 10 to the power minus 3. 10 to the power minus 3 is written as milliweber. So now we calculated the flux established in the iron core is 0.193 milliweber. Now we'll go to the second problem. A 100-turn coil is wound on a magnetic bar. The average diameter of the coil can be taken as equal to 10 millimeter. So this diameter is the diameter of the coil. Find the EMF induced in the coil when the flux density B is changed from 5 milliweber per meter square to 0.1 Weber per meter square in 35 nanoseconds. Now we'll see the data. What are the data available? So the number of turns is given 100 turns. The time taken to change the flux is 35 nanoseconds. That is 35 into 10 to the power minus 9. Nanosecond means 10 to the power minus 9. The diameter of the coil is 10 millimeter. So the radius is diameter divided by 2, 5 millimeter. So 5 into 10 to the power minus 3 meter. Millimeter is converted into meter. Then the flux is changing from two different value. First we will take this B1, it is 5 milliweber per meter square, that is 5 into 10 to the power minus 3. Milli is converted as 10 to the power minus 3 Weber per meter square. Milli is written as 10 to the power minus 3. And B2 changed to another value is 0.1 Weber per meter square. Now we need to find what is the EMF induced in the coil. So based on the given data, first we will find the area of cross section of the coil. A equal to pi r square. Pi into 5 into 10 to the power minus 3 the whole square. The radius of the coil. This is the radius of coil. So by simplifying this, what we got? 78.5 into 10 to the power minus 6 meter square. Area of cross section of the coil. Now from then we will find the flux. Flux density is given. From that we can able to find flux. Pi equal to B1 into A. So B equal to pi by A. So that pi equal to B into A. So pi 1 means B1 into A. The B1 is given as 5 into 10 to the power minus 3. The A is this value calculated 78.5 into 10 to the power minus 6. 5 milliweber per meter square given. So 5 into 10 to the power minus 3. So by simplifying, what we got? 0.3925 into 10 to the power minus 6 Weber. The flux in the first due to the first one. Similarly, the second flux pi 2 is nothing but B2 into A. The B2 value is given as 0.1 into this area 78.5 into 10 to the power minus 6. So by simplifying this, what we got? 7.85 into 10 to the power minus 6 Weber. The pi 2 also we calculated the pi 2 value. Now the change in flux, the difference between these two, pi 2 minus pi 1, 7.85 into 10 to the power minus 6 minus 0.3925 into 10 to the power minus 6. These two values, pi 2 minus pi 1. So the resultant will be 7.4575 into 10 to the power minus 6 Weber. The change in flux is nothing but this value. So by using that, we can find the EMF induced in the coil. EMF induced in the coil equal to N into d pi by dt. Number of turns into rate of change of flux. So the number of turns is 100 into this change in flux is nothing but d pi 2 minus pi 1. So 7.44575 into 10 to the power minus 6. Divided by the t, time is given 35 nanoseconds. So 35 into 10 to the power minus 9. So by simplifying, we got 21.307 into 10 to the power 3. So this 10 to the power 3 we can multiply that, so that 21,307 voltage. The EMF induced in the coil is 21,307 volt. The more problem available in other videos, the link is given in the description box, and also subscribe the channel for more electrical videos. Thank you. Welcome viewers. In this video, we will see the solved problem in magnetic circuit part 5. Subscribe this channel for more videos related to the electrical and course material. The course material drive link available in the description box. Now we will go to the first problem. Calculate the inductance of a coil of 400 turns wound on a iron cored toroidal ring having mean diameter of 30 cm. The ring has a circular cross section of diameter 5 cm. Also calculate the EMF induced in the coil when the current of 4 ampere is reversed in 30 milliseconds. So we need to find the EMF induced in the coil. Now we will see the data. What are the data available? The number of turns is 400. Mean diameter given is 30 centimeter. So that radius equal to 30 divided by 2, 15 centimeter. So from this radius we can find the length of the magnetic path. The length is nothing but circumference because it is a circular ring. So the length is nothing but the circumference of the ring. So 2 pi r, r value is given. So 2 into pi into r is 15 into 10 to the power minus 2. So that By simplifying, we got 30 pi into 10 to the power minus 2. That is nothing but 0.942 meter. The length of the magnetic path is 0.942 meter. It is calculated from circumference. Then diameter is given as 5 centimeter. This is nothing but diameter of the coil. This is the radius, nothing but radius of the core, iron core. This is the diameter of the coil. So that radius equal to diameter by 2, 5 by 2 is 2.5, centimeter is given, so multiplying minus 2 we can convert into meter. 2.5 into 10 to the power minus 2 meter. From that we can calculate the area pi r square. Pi into r square, 2.5 into 10 to the power minus square, so that 1.963 into 10 to the power minus 4 meter square. So this is the area of the coil. This radius refers radius of the iron core. This radius refers radius of the coil. And air cored coil is given. So mu r, relative permeability in case of air is 1. And the absolute permeability is 4.5 into 10 to the power minus 7, constant. Now we'll go to the problem. First we will find the inductance. L equal to n pi by I. It's a general formula, number of turns flux divided by I. The pi can be written as Ni by S, that is flux equal to mmf divided by reluctance. Then the original formula is reluctance equal to Ni by pi. From that we calculated the flux. Now we can substitute this pi here, so that n by I into the pi is replaced as Ni by S. So this I got cancelled. So what we got, n square by S. That S one more formula is L divided by mu naught mu r into A. The formula, the reluctance can be written as length divided by mu naught mu r into A. So these three terms will go to the numerator. So that n square mu naught mu r A divided by L. Now we'll substitute the values in this. So n square is 400, n is 400, number of turns is 400, 400 square, mu naught is 4 pi into 10 to the power minus 7 into 1, the mu r is 1 because of air. The area calculated as 1.963 into 10 to the power minus 4 and the length is 0.942. By simplifying this we got 4.1877 into 10 to the power minus 4 Henry. So now the inductance is calculated. Our aim is to find the EMF induced. So the current is given as 4 ampere reversed. So the difference between these two current is 4 ampere, thereafter reversed means minus 4. Originally 4, that is again in that it is reversed. Current is reversed means plus 4 to minus 4. So the difference between the current is 4 minus of minus 4. So it becomes 4 plus 4, 8 ampere. Current is reversed from plus 4 to minus 4. So that while finding the difference we got 8 ampere. The current is the time is given as 30 milliseconds. So 30 into 10 to the power minus 3, milli means 10 to the power minus 3 seconds. So now we can substitute this value. So EMF induced is nothing but L di by dt. We know the value of L, di and dt, so that we can use this formula. So the L calculated as 4.1877 into 10 to the power minus 4 into the current is 8 ampere. The time is 30 into 10 to the power minus 3. So by simplifying this, what we got, 0.1117 voltage. The EMF induced is 0.117 voltage. Now we'll go to the second problem. A coil has a self inductance of 30 millihenry. Calculate the EMF induced in the coil when the current in the coil is increased at a rate of 300 ampere per second, raised from 0 to 10 ampere in 0.06 second. Right? The inductor value is given. We need to find the EMF. Two different cases available. One is increased at the rate 300 ampere per second. Another one raised from 0 to 10 ampere at 0.06 seconds. So the L is given 30 millisecond. millihenry. So that is 30 into 10 to the power minus 3 Henry. Milli means 10 to the power minus 3. So that the EMF equal to E equal to L di by dt. The L value is 30 into 10 to the power minus 3. What is di by dt? The current is increased at the rate. So di by dt is nothing but 300 ampere per second. Di by dt. I by dt means ampere per second. So this value is given. The rate of increase is 300. So 30 into 10 to the power minus 3 into 300 will give 9 voltage. For the first case, it is 9 voltage. That is, current is increased at the rate 300 ampere per second. Now we'll go to the second case. The current is increased from 0 to 10 ampere. So that di equal to 10 minus 0, 10 ampere. The dt is 0.06 second. Right? Here di by dt is directly given 300 ampere per second. Here di is given and dt is given separately. So E equal to L di by dt. Now we can substitute the value. So that E equal to L is 30 into 10 to the power minus 3. The current is 10 ampere. The time is 0.06. So by simplifying, we got 5 voltage. So for the second case, the EMF induced is 5 voltage. Now we'll go to the third problem. Two identical coils A and B, each having 1000 turns, lie in the parallel plane such that 60% of flux produced by the one coil linked with the other. Each having 1000 turn, 60% of flux is linking from one coil to other coil. The current is 10 ampere in coil A, produces in it a flux of 10 to the power minus 4 Weber. If the current in the coil A changes from plus 12 ampere to minus 12 ampere in 0.02 seconds, what would be the magnitude of EMF induced in the coil B, second coil? Right? Now we'll see the given data. So for N1 and A2, in the both the coil, the number of turns is 1000. The current in the first coil is given 10 ampere. The flux in the first coil is given 10 to the power minus 4 Weber. And one more data is given, 60% of coil is linked. So the amount of flux linking the second coil is pi 1 to equal to 60%, 0.6 into this pi 1, 10 to the power minus 4. So pi 1 equal to 10 to the power minus 4. In that 60% is linking with the second coil. So pi 1 to equal to 60% into pi 1. Now we'll find the di1 by dt. The current in the first coil is given. So di1 by dt equal to 12 ampere. Then it is reversed into minus 12. So the changed from plus 12 to minus 12. So while finding the difference, 12 minus of 12. So it become 12 plus 12, 24. The current is changed from plus 12 to minus 12. So the rate of the change in value will be 24. And the current is 0.02 seconds. So by simplifying, what we got, 1200 ampere per second. So the rate of change of current in the first coil. But the question is asked EMF induced in the second coil, coil B. So by using the mutual inductance formula, we can find the EMF induced in the second coil, that is M di1 by dt. So the EMF induced in the second coil is based on the current rate of change of current in the first coil. That is the property of the mutual inductance. So this value is given, so you can easily find the current in the first coil is given, so you can easily find the EMF in the second coil by using this formula. So the M can be written as N2 pi 12 divided by I1. Here also we have N2 is available, pi 12 also available, divided by I1. So the mutual inductance in the second coil based on the current in the first coil. So due to this property, we can use this formula. Then di1 by dt. Now all the values are available. So the N2 is 1000, pi 12 we calculated 60% of pi 1 divided by I is 10 ampere into di by dt we calculated 1200. So by simplifying, we got 7.2 voltage EMF induced in the second coil due to current change in the first coil. So now we calculated the EMF. So 3 problems solved in this. More problem in the magnetic circuit available in separate video. The link is available in the description box. Also subscribe the channel for more electrical videos. Thank you. Welcome viewers. In this video, we'll see the solved problem in magnetic circuit part 6. Subscribe this channel for more electrical videos and course material. Course material drive link is available in the description box. Now we'll go to the first problem. Calculate the magnetomotive force required to establish a flux density of 1.3 Weber per meter square in the 2 millimeter air gap electromagnet having an iron path of 2 meters. Take the relative permeability of the iron as 1500. Neglect the leakage flux. So we need to find the flux density. We need to find the magnetomotive force. The air gap available and the iron path also available. Now we'll see the given data. So the magnetic flux density is given 1.3 Weber per meter square. The mu naught is constant, absolute permeability 4 pi into 10 to the power minus 7. The length of the air gap is 2 millimeter. So it is 2 into 10 to the power minus 3 meter. The length of the iron path is 2 meter. And mu r of the iron is given as 1500. Mu r of air, in case of air, it is always 1. The value is 1. So we need to find the MMF, magnetomotive force. First we start from the flux. So pi equal to Ni by S. The formula is S equal to Ni by pi. Reluctance equal to Ni divided by pi. From that pi equal to Ni divided by S. So that is equal to Ni divided by. So the reluctance, we have two different paths available. One is iron path and the air path, air gap. So the S is nothing but L divided by mu naught mu r into A. That is a general formula. So this is for iron, this is for air. So this A is available commonly, so that can be brought in the numerator. It is available in denominator, that is brought into numerator. So that Ni A divided by this term. Now this A is brought into the left hand side, pi by A. That is equal to Ni divided by this reluctance. So this pi by A is nothing but flux per unit area is nothing but flux density. So that can be written as B. B equal to Ni divided by this reluctance. Now we'll go for the further simplification. So that can be written as Ni equal to B into reluctance path. It is cross multiplied. So what we need is Ni. Ni is nothing but total MMF. Our aim is to find the total MMF, that is nothing but N into I. So that is cross multiplied and given in the term. So the B is available 1.3 Weber per meter square. The length of the iron path is 2 meter. The length of the air gap is 2 millimeter. So 2 into 10 to the power minus 3. Then mu naught is constant 4 pi into 10 to the power minus 7. For iron, the relative permeability is given 1500. So here mu naught is 4 pi into 10 to the power minus 7. The mu r A equal to 1. So after simplifying this, we got 3448.3571 ampere turns. The total MMF for this circuit is 3448.3571 ampere turns. Now we'll go to the second problem. An iron ring of circular cross section 5 centimeter square have a mean circumference of 200 centimeter. The iron ring cross sectional area, this is the circumference. It has a shock cut of 2 millimeter length and it would wound with a 400 turns of wire. Right, 2 millimeter air gap is available and the number of turns is 400. Find the exciting current when the flux in the air gap is 0.5 milliweber. Take mu r for the iron is 600 and the lambda leakage flux equal to 1.2. The leakage flux given as 1.2. Now we'll see what are the data given. So the area is given 5 centimeter square. While converting meter, 5 into 10 to the power minus 4 meter square. The circumference is given as 200 centimeter, that is 200 into 10 to the power minus 2 meter. So the circumference is nothing but length. Because of this iron ring circular form, the circumference and length are equal. So the length of the iron path can be taken as this circumference, 200 into 10 to the power minus 2 meter. The length of the air gap is given, it is 2 millimeter. So that 2 into 10 to the power minus 3 meter. Right. The number of turns is given 400. The relative permeability of iron is 600. Relative permeability of the air is 1, is always 1. The leakage flux is given as 1.2, lambda equal to 1.2. We know that mu naught value is 4 pi into 10 to the power minus 7. And the flux in the air gap is given 0.5 milliweber. So that is equal to 0.5 into 10 to the power minus 3 Weber. Milli means you have to multiply with 10 to the power minus 3. Right. So we need to find the value, the exciting current value. First we will see the flux. The flux linking with the iron ring. Pi iron equal to pi air into lambda. So the formula is flux linkage equal to pi iron divided by pi r. From that pi iron equal to pi air into lambda, because we need to find this, the flux in the iron core. So that is 0.5 into 10 to the power minus 3 into the leakage flux coefficient is given as 1.2. So the flux in the iron is 0.6 into 10 to the power minus 3 Weber. Now we will go to the current value. So Ni mmf equal to pi iron into L iron divided by mu naught mu r iron into A. The formula is available, based on that we can write. So the total mmf equal to mmf due to the iron path and mmf due to the air path. So it is given, terms are given. So the here what we need is only the current. So bring this, the number of turns in the denominator, 1 divided by n into this value, pi iron flux in the iron core, the length mu naught mu r iron into area. Similarly pi flux in the air, length of the air gap, mu naught mu r A into A. Now we will substitute the value. So the number of turns given as 400. The flux in the pi, now it is just now we calculated 0.6 into 10 to the power minus 3. The length is given 200 into 10 to the power minus 2. 200 centimeters, it is 200 into 10 to the power minus 2. The mu naught is 4 pi into 10 to the power minus 7. Then iron ring is given as 600. Then area 0.5 into 10 to the power minus 4. The flux in the air gap is given 0.5 milliweber. So 0.5 into 10 to the power minus 3. The length of the air gap is given 2 millimeter. So 2 into 10 to the power minus 3 divided by mu naught is 4 pi into 10 to the power minus 7. Mu r of air is 1. For always the relative permeability of air is 1. And the area is 5 into 10 to the power minus 4. So by simplifying this value, what we got, 11.937 into 7 ampere. So the area is nothing but, it's not 0.5, it is 5 only. So it's a 5 into 10 to the power 4. So by simplifying that, what we got, 11.937 ampere. So now we calculated the exciting current. So for more problem available in separate video, link is given in the description box. Also subscribe the channel for more videos. Thank you.